Before we get into this story, it's worth clearing something up directly, because there's a version of this headline circulating online that isn't accurate. You may have seen claims that James Webb just captured the first real image of Betelgeuse, or that Webb detected the star's final moments before supernova. Those specific claims trace back to low-quality blog networks that have been recycling the same unverifiable text across multiple channels, with no actual NASA release, peer-reviewed paper, or named institution behind them anywhere. What actually happened, and what's genuinely remarkable, is a real discovery, correctly credited to a different telescope entirely. In January 2026, astronomers announced they had finally found direct evidence of something suspected for years, but never confirmed. A hidden companion star, orbiting so close to Betelgeuse that it's actually carving a visible wake through the giant star's own outer atmosphere. And the instrument responsible for catching that wake wasn't Webb, it was Hubble, working alongside ground-based observatories in a genuinely satisfying resolution to one of the most persistent mysteries surrounding the most famous dying star in the night sky. This is the real story of what astronomers actually found at Betelgeuse, correctly attributed, and why it finally explains decades of the star's strange, unpredictable behavior. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why finding this companion star mattered so much to the scientists who found it, you first need to understand exactly what makes Betelgeuse such a genuinely unusual, closely watched object in the first place. Sitting roughly 650 light-years from Earth in the constellation Orion, easily visible to the naked eye as the bright reddish star marking the hunter's shoulder, Betelgeuse is a red supergiant of truly extraordinary size, large enough that if you replaced our own sun with it, its outer layers would extend out past the orbit of Mars, potentially reaching as far as Jupiter, large enough in total volume to contain more than 400 million suns. It's also, by stellar standards, genuinely old, having burned through most of its available nuclear fuel, and it sits somewhere in the final stages of its life, destined to eventually collapse and explode as a supernova, though the exact timing of that event remains genuinely uncertain and could still be anywhere from tomorrow to tens of thousands of years away. Because it's both enormous and relatively close to Earth, Betelgeuse is one of the very few stars whose surface and surrounding atmosphere can actually be studied directly, rather than simply observed as an indistinct point of light, making it one of astronomy's most valuable and most closely watched natural laboratories for understanding exactly how massive stars behave as they approach the end of their lives, unlike the vast majority of stars in the night sky, which appear as nothing more than fixed, unchanging points of light regardless of how powerful a telescope you use to study them. Betelgeuse's sheer physical size and proximity mean astronomers have actually been able to resolve real surface detail on the star itself, tracking bright and dim patches, changes in shape and shifts in its outer atmosphere over time, the kind of dire CIT stellar surface observation that remains essentially impossible for almost every other star beyond our own sun. That unique observational access is exactly what makes Betelgeuse such a valuable long-term research target, and exactly why any unexplained pattern in its behavior tends to attract sustained, serious scientific attention rather than being dismissed as unremarkable stellar noise. Astronomers have been tracking Betelgeuse's brightness and behavior for well over a century, using it as a kind of natural benchmark for studying how the very largest stars behave as they age, and what they've found has consistently defied easy explanation. Interest in the star surged dramatically in late 2019 and early 2020, when Betelgeuse unexpectedly dimmed to roughly a third of its normal brightness, the most significant dimming event ever recorded for the star, dramatic enough to be noticed by casual skywatchers without any equipment at all. The event sparked genuine public speculation that Betelgeuse might be on the verge of going supernova, headlines that spread quickly across news outlets and social media at the time. The actual explanation, worked out through subsequent research using Hubble and other observatories, turned out to be something researchers have since informally described as a stellar sneeze, a sudden, massive ejection of material from the star's surface that cooled and condensed into a dust cloud, temporarily blocking a portion of the star's light from reaching Earth from our specific vantage point, rather than any indication the star was actually approaching its final collapse. That event alone generated years of dedicated follow-up research, but it sat alongside a second, quieter, longer-running mystery that had puzzled astronomers for far longer. Beyond the dramatic 2019 dimming event, scientists had identified two separate recurring cycles in the star's ongoing variability, each operating on a genuinely different timescale and, as it turned out, a genuinely different underlying cause. The first, A shorter cycle lasting about 400 days was generally linked to internal pulsations within the star itself, something close to a natural stellar heartbeat. The star's outer layers rhythmically expanding and contracting as internal pressure and gravity trade off against each other, a well understood phenomenon observed in many pulsating giant stars throughout the galaxy. The second, a much longer, considerably more puzzling cycle, lasting approximately 200 days, or roughly 6 years, resisted easy explanation for years. Unlike the shorter pulsation cycle, this longer pattern didn't fit cleanly into the standard models describing how a star's internal structure alone should cause its brightness to vary over time. And it became one of the more persistent, unresolved questions in the ongoing effort to fully understand Betelgeuse's behavior. Researchers had proposed several different explanations over time to try to account for that longer 2100-day cycle, and it's worth walking through why each of the leading candidates ultimately fell short, because that process of elimination is part of what makes the eventual answer so satisfying. Some researchers suggested the cycle might be driven by massive internal convection cells, essentially giant currents of superheated material churning beneath the star's surface, similar in basic principle to convection patterns seen on the Sun, but operating on a vastly larger scale given Betelgeuse's enormous size. The problem with this explanation was that convection cells, as understood through existing stellar models, generally shouldn't produce a cycle this long, this regular, or this consistent over the many years astronomers had already been tracking it. Others proposed clouds of dust periodically forming in the star's outer layers and then dispersing again, a mechanism plausible enough on its own but difficult to reconcile with the specific, repeating regularity of the observed cycle. Still others pointed to some form of underlying magnetic activity, similar to the magnetic cycles that drive periodic changes in our own sun's behavior, though Betelgeuse's magnetic field, if it has one at all in any organized sense, remains poorly understood compared to the sun's. And running alongside all of these was a persistent, recurring hypothesis that had been gaining real traction among researchers for several years. The possibility of a hidden companion star, a smaller star orbiting deep within Betelgeuse's own extended outer atmosphere, its gravitational and physical presence periodically disturbing the giant star in a way that could plausibly produce the observed cycle. This hypothesis had a specific appeal that the other candidates lacked. If a companion star existed, its orbital period would naturally explain why the cycle was so consistent and so regular, repeating with the same underlying rhythm, the same way any orbiting object repeats its path around a central body. One earlier research group had even reported a possible tentative detection consistent with this idea, but without direct, unambiguous physical evidence actually confirming a companion's presence, the hypothesis remained exactly that. An unproven theory, one candidate explanation sitting alongside several other plausible alternatives, without anything close to genuine scientific consensus behind it. The team that finally resolved this question, led by Andrea Dupree, an astronomer at the Center for Astrophysics, Harvard, and Smithsonian, took a patient, methodical approach that ultimately paid off. Rather than trying to directly image an extremely faint companion star sitting immediately adjacent to one of the brightest, most overwhelming objects in the night sky, an approach that would have been genuinely difficult given how completely Betelgeuse's own light would drown out any nearby companion, the team. Instead, spent nearly 8 years carefully tracking subtle, indirect changes in Betelgeuse's own light and behavior, using observations from NASA's Hubble Space Telescope, combined with additional data gathered from the Fred Lawrence Whipple Observatory and the Roque de los Muchachos Observatory. By combining these different sources, the team identified consistent, repeating patterns in Betelgeuse's spectrum, meaning the precise breakdown of colors and wavelengths present in its light, along with corresponding shifts in the motion of gas within the star's own outer atmosphere. What those patterns revealed was a wake, a genuine physical trail of denser, disturbed gas, forming specifically as a companion star moves directly through Betelgeuse's own extended outer atmosphere. Dupree described the underlying physical picture using a simple, intuitive comparison. It's a bit like a boat moving through water, she explained, with the companion star creating a real visible ripple-y effect in Betelgeuse's own atmosphere, one the team could now actually see directly, translated into the language of shifting spectral data rather than a literal photograph. pH. The wake itself, according to the team's analysis, consistently appeared shortly after the companion star passed in front of Betelgeuse from Earth's perspective, occurring approximately every 200 days, precisely matching the long-standing, previously unexplained cycle astronomers had been tracking in the star's brightness for years, and aligning closely with what earlier theoretical predictions had already proposed for exactly this kind of hidden companion. Dupree was direct about what made this specific finding so significant compared to everything that came before it. The idea that Betelgeuse had an undetected companion had been gaining genuine popularity as an explanation over the preceding several years, she noted, but without direct evidence. It remained fundamentally an unproven theory, one hypothesis, competing against several others without any way to definitively settle the question. This newly detected wake changed that. For the first time, she said, researchers were seeing direct signs of this trail of gas, real physical confirmation that Betelgeuse genuinely does have a hidden companion actively shaping its appearance and its behavior, rather than one plausible theory sitting alongside several equally plausible alternatives. The team formally named this newly confirmed companion star Siwara. It's important to understand exactly how dramatic the size difference between these two stars actually is, because it helps explain why direct imaging had never worked as a detection method in the first place, and why so many earlier attempts to confirm a companion had come up short. Compared to Betelgeuse, an object hundreds of times larger, the companion star would be little more than a pinprick, an object so comparatively tiny and so thoroughly overwhelmed by its massive neighbor's overwhelming light that photographing it directly at this distance, using any current telescope technology, simply wasn't a realistic option. Even Webb, for all its extraordinary infrared sensitivity, faces the same basic physical problem here that every other instrument does. Betelgeuse itself is bright enough and close enough to its own suspected companion that isolating a faint secondary star sitting almost directly in front of an overwhelmingly brighter one remains a genuinely difficult observational challenge, not meaningfully solved simply by using a more powerful telescope. That's precisely why Dupree's team pursued an entirely different strategy. Rather than trying to isolate a point of light, they tracked the physical consequences of the companion's presence instead, the way its passage disturbed the surrounding gas, producing effects detectable through careful spectroscopy, even when the object producing them couldn't be directly photographed at all. This approach, examining the star's spectrum, the precise breakdown of colors and wavelengths present in its light, deserves a little more explanation because it's the specific tool that made this whole discovery possible. When astronomers analyze a star's spectrum in detail, they're not simply measuring its overall color or brightness. They're examining the precise pattern of light absorbed and emitted by the various elements and gases present in and around the star, along with subtle shifts in the exact wavelength of that light caused by the motion of the material producing it, a phenomenon called the Doppler effect. The same basic principle that causes a passing ambulance siren to shift in pitch as it moves toward or away from you. By tracking how these specific wavelength patterns shifted and changed over the roughly 8 years of the study, the team could effectively reconstruct the motion and behavior of gas within Betelgeuse's atmosphere in remarkable detail, detecting the specific signature of a disturbance moving through that gas, even without ever capturing a literal photograph of whatever was causing it. Confirming Siwara's existence required exactly this kind of patient, indirect, multi-instrument detective work, tracking subtle changes in light and gas motion over the better part of a decade, cross-referenced against multiple independent observatories to rule out instrumental error or coincidence, rather than attempting the far more difficult task of a single direct photograph. This discovery does more than simply satisfy years of scientific curiosity about one specific star's unusual behavior. It genuinely resolves one of the most enduring, actively debated puzzles surrounding Betelgeuse, and in doing so, gives astronomers something considerably more valuable than a single answered question. Dupree explained the broader significance directly. With this new evidence in hand, Betelgeuse now offers researchers what she described as a front row seat to watch how a giant star changes over time. Finding the wake left by its companion, she explained, means scientists can now begin to genuinely understand how stars like this evolve, shed material, and eventually explode as supernovae insight that extends well beyond Betelgeuse itself, potentially helping explain similar, previously mysterious, long-term variability observed in other giant and supergiant stars scattered throughout the galaxy. The findings were formally announced at a news conference during the 247th meeting of the American Astronomical Society in Phoenix, and the underlying research has been accepted for publication in the peer-reviewed Astrophysical Journal, giving this discovery the same rigorous scientific vetting applied to any major finding in the field, rather than existing as a casual announcement without formal backing. There's also a genuinely satisfying next chapter already built into this story, and it's worth understanding because it shows exactly how confident researchers are eyeing their own findings. From Earth's current perspective, Betelgeuse is presently in the process of eclipsing its own companion star, meaning Siwara has temporarily moved into a position where it's obscured from view. Astronomers are already planning additional dedicated observations for when the companion becomes visible again, expected sometime in 2027, specifically to gather further direct evidence and continue refining exactly what they've learned about this system. That kind of concrete, scheduled follow-up plan is exactly the sort of thing that distinguishes a genuine, confident scientific finding from a speculative one. Researchers aren't simply claiming victory and moving on. They're actively planning how to keep studying this specific system further, precisely because they're confident there's real, additional science still to learn from it. It's also worth placing this discovery within the broader context of what astronomers already understood, and didn't understand about Betelgeuse's eventual fate, because Siwara's confirmation genuinely adds a new layer to that ongoing story rather than replacing it. Betelgeuse remains, by every current estimate, on a trajectory toward an eventual supernova, the explosive death that awaits every star of sufficient mass once it exhausts the nuclear fuel in its core. When that happens, it will be genuinely spectacular from Earth's perspective, potentially visible in broad daylight and easily bright enough to cast shadows at night for a period of weeks. An event astronomers have been anticipating and preparing to study for years, given how relatively close and well-studied this particular star already is. But the timing of that eventual explosion remains genuinely uncertain, and nothing about the Siwara discovery changes that timeline in either direction. What it does change is astronomers' ability to understand the specific processes happening inside and around Betelgeuse right now, in the years and decades leading up to that eventual event, since a close companion star physically moving through a supergiant's outer atmosphere would plausibly affect how that atmosphere sheds material over time, a genuinely relevant detail for understanding exactly how much mass Betelgeuse might lose, and how its outer structure might evolve in whatever time remains before it eventually goes supernova. This also connects to a broader pattern astronomers have increasingly recognized across other massive aging stars throughout the galaxy. Many red supergiants display similarly puzzling long-term brightness variations that have never been fully explained, and Dupree's team has explicitly noted that the technique used to confirm Siwara, tracking indirect spectroscopic evidence of a companion's gravitational and physical influence rather than attempting direct imaging, could plausibly be applied to other similarly mysterious stars as well. If hidden, low-mass companions turn out to be a more common feature of evolved massive stars than previously appreciated, simply difficult to detect using conventional methods. That would represent a genuinely significant shift in how astronomers understand the later stages of stellar evolution more broadly, not just for Betelgeuse specifically, but for an entire category of aging giant stars scattered throughout our galaxy and beyond. It's worth being clear and direct, one more time, about separating this real, well-documented discovery from the Fabricate D claims circulating elsewhere online. This finding did not come from the James Webb Space Telescope. It came from NASA's Hubble Space Telescope, in collaboration with ground-based observatories led by a named verifiable researcher at a real established astrophysics institution, and it was announced at a real scientific conference before being accepted into a real peer-reviewed journal. Nothing about this discovery involves Betelgeuse's final moments, an imminent supernova, or any kind of urgent countdown. What it actually involves is a patient, nearly decade-long process of careful observation, finally producing direct, confirmed evidence for a companion star that astronomers had suspected but couldn't prove for years. That distinction matters not just for getting the credit right, but because it reflects something genuinely important about how real astronomical discoveries actually happen, slowly, carefully, through years of accumulated data and multiple independent lines of evidence, rather than through a single dramatic photograph appearing overnight. It's also worth noting that Webb has, in fact, studied Betelgeuse before, just not in the way the fabricated headlines describe. Webb's infrared instruments have contributed to broader studies of the dust and material surrounding evolved, mass-losing stars like Betelgeuse in the years since it became operational, work that complements, rather than competes, with Hubble's own contributions to understanding this star. The real story of Betelgeuse research has never been about one single telescope claiming a dramatic, singular breakthrough. It's been a genuinely collaborative, multi-decade effort involving Hubble, ground-based observatories around the world, and yes, Webb as well, each contributing different pieces of a much larger, ongoing scientific picture, exactly the kind of patient, cumulative process that real astronomy actually looks like, even when it doesn't produce the kind of single, dramatic headline moment that fabricated stories are designed to manufacture. So here's where this genuinely leaves things, honestly, grounded entirely in NASA's own published statements and the research team's direct on-the-record quotes. Betelgeuse, one of the most closely watched, most famous stars in the entire night sky, has a confirmed companion star, Siwara, whose orbit carries it directly through the giant star's own outer atmosphere roughly once every 6 years, generating a physical wake of disturbed gas that finally, definitively explains a puzzling brightness cycle astronomers had tracked without a confirmed cause for years. That confirmation came from Hubble, not Webb, through nearly 8 years of careful, indirect, multi-observatory detective work, rather than any single dramatic photograph, and it offers genuine scientific insight into exactly how massive, aging stars like Betelgeuse behave as they approach the final stages of their lives, insight astronomers are already planning to build on further when Siwara becomes observable again in 2027. If this kind of story is what you come here for, one grounded in exactly what NASA's own scientists measured, confirmed, and correctly credited, rather than fabricated viral claims, hit subscribe and turn on notifications, because there's clearly more genuine mystery in the real universe than any invented headline could ever offer. Drop a comment telling me whether you'd seen the fabricated web version of this story before, and share this with someone who deserves the real discovery instead of one built from nothing.